Henry Becquerel placed a piece of uranium ore over sealed unexposed photograph. That is, he put the photograph in an envelope and the photograph was not exposed and placed it in a drawer below a piece of uranium ore. Days later, the photograph was exposed, even though it was never subjected to any light. Henry's conclusion was that radiation emitted by the uranium ore has caused the exposure of the photograph. Marie and Pierre Curie said that this radiation is natural radiation emitted by the uranium because of the instability of its nucleus. Ernest Rutherford pioneered in experiments of nuclear bombardment and introduced the word transmutation. Transmutation, as it was in alchemy, is the changing of a nucleus of an atom to another nucleus, and this is because the nucleus is unstable and wants to achieve stability. So, Henry Becquerel placed uranium ore over unexposed photograph and the photograph was exposed. Marie and Pierre Curie called this natural radiation because the uranium was unstable. And Ernest Rutherford introduced transmutation, or the changing of one nucleus into a more stable one. Now moving on to types of radiation. Alpha radiation, or alpha decay, happens when a nucleus has an atomic number greater than 83. That is, it has too many neutrons and too many protons. It emits an alpha particle. An alpha particle is 2 neutrons and 2 protons, and that is a helium nucleus. Now, here, this radium emitted 2 protons and 2 neutrons. So, its atomic number decreases by 2 and its atomic mass decreases by 4. In alpha decay and all types of nuclear reactions, atomic number and atomic mass are conserved. However, mass is not conserved because mass and energy are equivalent. So, atomic number decreases by 2, while atomic mass decreases by 4, and on both sides of the reaction, atomic number and atomic mass are conserved. Sometimes atoms have too many neutrons and too little protons. In these cases, a neutron breaks into a proton, electron, and antineutrino. So a neutron becomes a proton, an electron, and a small antineutrino. The electron and the antineutrino are released from the atom or the nucleus. The electron is fast moving and is called a beta particle. So the electron and the antineutrino leave the nucleus. The neutron becomes a proton. So we have lost a neutron but gained a proton. So the mass number does not change. However, because we gained a proton, the atomic number increases by 1, and on both sides, atomic mass and atomic number are conserved. A positron is a positive electron. It has the charge of a proton, it has a positive charge, and the small mass of an electron. Sometimes a proton changes into a neutron, a positron, and an antineutrino. The positron and antineutrino are emitted from the nucleus and the neutron stays. Now, because we lost a proton but gained a neutron, the atomic mass does not change. However, the atomic number decreases by 1, and on both sides, atomic mass and atomic number are conserved. So, in alpha decay, atomic mass decreases by 4 and atomic number decreases by 2. In beta and positron decay, atomic mass doesn't change. In beta decay, atomic number increases by 1, and in positron decay, atomic number decreases by 1. So, in beta and positron decay, atomic mass does not change. In beta decay, atomic number increases by 1, and in positron decay, atomic number decreases by 1. And in all cases, atomic number and atomic mass are conserved on both sides of the equation. Sometimes a proton is converted into a neutron and an electron is captured into the nucleus. So the nucleus has gained an electron. Its atomic mass does not change, while the atomic number decreases by 1. And on both sides, atomic mass and atomic number are conserved. This is the opposite of beta decay, because in beta decay, a nucleus loses an electron. In electron capture, it gains an electron. Atomic mass, like in beta decay, doesn't change. However, atomic number decreases by 1. The last type of decay is gamma decay. In gamma decay, a gamma photon, a small gamma ray, is released from the atom. No particles, no alpha particles, no electrons, no protons, no particles are emitted from the nucleus. Only energy is emitted, so energy is lost. Gamma decay is the most penetrating and harmful radiation. Now, since mass and energy are equivalent, the loss of energy in gamma decay causes a loss in mass, so mass decreases. However, mass number and atomic number do not change. Over here, energy was released with the gamma photon. However, the mass number and the atomic number do not change. The total mass decreases because energy was released from the nucleus. Now, to wrap things up, alpha decay could be stopped by a sheet of paper or even your skin. Alpha decay disintegrates within a small distance over a short time. Alpha decay carries the greatest mass but has the least energy. Beta decay is less massive and faster than alpha decay, and beta, of course, comes with positron. Beta and positron could be stopped by a thin sheet of aluminum foil. However, they are more penetrating than alpha. Gamma can be stopped by centimeters thick lead or very thick concrete. Gamma is the fastest and has no mass at all. So, the fastest is gamma. The most massive is alpha. The slowest is alpha. The least massive is gamma. Gamma is the most penetrating and dangerous. It could cause instant cancer. Alpha could be stopped by a thin sheet of paper or even your skin. Beta is stopped by a thin sheet of aluminum foil. Gamma is stopped by centimeters thick lead or very thick concrete. The fastest is gamma. And the most mass is found in alpha, with its 2 protons and 2 neutrons. The most penetrating and most dangerous is gamma. That's all. Do not forget to subscribe, like, and always achieve more. Thank you.